Welcome. We are using Octave to look at some of the problems of phase separation, regular solution model and so on, and we are planning to use Octave to solve the classical diffusion equation. And as part of this exercise, the first thing that we want to do is to non-dimensionalize. Remember, we had the free energy expression, for example, the free energy of mixing for the regular solution as omega x 1 minus x plus RT x logarithm of x plus 1 minus x logarithm of 1 minus x. So, what we did first was to non-dimensionalize this equation, because see this is free energy, and so every term, then this is some high school physics probably you have learned, that they should all have the same units or dimension. If this is energy, this also has to be energy, this also has to be energy. And look at these terms. So, this is x ln x plus 1 minus x ln 1 minus x, where this is the fraction of B atoms, x is the fraction of B atoms to the total number of atoms. So, that is just a number, it does not have any units, which means all the unit is carried by RT in this case and omega in this case. So, what we did was to take RT as the parameter, using which we will non-dimensionalize this entire equation, and which is what we did. We call this as delta G by RT as omega by RT, for which we gave a shorthand notation called alpha, x into 1 minus x plus x ln x plus 1 minus x ln 1 minus x. So, all our computations for the free energy was done using such a non-dimensional expression. Now, we are going to do the next non-dimensionalization, which is for the partial differential equation, which is the so called Fick's second law. Okay. We have derived this equation. So, I am going to write the one dimensional version of the equation and non-dimensionalize that equation. Okay. So, the equation is something like that: rate of change of concentration is equal to d, I have assumed the diffusivity to be a constant, del squared C by del x squared. Okay, so, what are the quantities which are dimensional here? So, you can assume that the concentration to be a number, okay, again like x. So, we will not worry too much about it, or even if you put some dimension, like this is per mole say, and this per mole and this is also per mole. So, both sides it will be cancelled out. So, let us not bother about the dimension for C. The other quantities that have dimension is that t, which is time, has the dimension of time, and x, which is position, has the dimension of length. And then we have diffusivity, which is generally given in meter squared per second. Then that means it has L squared T inverse as its dimension. What we are going to do is that we are going to consider some characteristic time, because time and length are the only basic dimensional quantities that we have. D is basically a derived quantity. So, all that I need to do is to choose two quantities, one that refers to the characteristic time scale, the other one which refers to the characteristic length scale, that is sufficient for me to non-dimensionalize this equation. Okay. So, that is what we are going to do. So, let us again take the equation. So, this is the Fick's second law. So, that is dou C by dou T is equal to d del squared C by del x squared. So, I am going to take a characteristic time as tau, and I am going to take a characteristic length L0. What are these quantities? We will discuss them. So, I am going to take these and I am going to scale all the times by tau and all the lengths by L naught. So, let us do that. So, if I take dou c by dou t by tau, so I have divided by tau, so I will have 1 by tau is equal to d del squared c by del x by L naught squared. So, which means L naught squared will come here. Okay. So, let us call the non-dimensional quantities t by tau, now it is non-dimensional, it is like a number, right, it has seconds, this has seconds, so that got cancelled out. So, you will have dou c by dou t prime, the primed quantities are non-dimensional, is equal to d tau by L naught squared. Notice that this quantity also now got non-dimensionalized, because d is meter squared per second, L naught squared will have meter squared, tau will have second. So, everything will cancel. So, you will have a d prime to indicate that this is non-dimensional diffusivity, that will be dou squared c by dou x prime squared. Okay. So, let me write the non-dimensional version of the equation once more. So, what do we have? We have dou c by dou t prime is equal to d prime del squared c by del x prime squared. Okay. Typically, people choose sometimes the non-dimensional diffusivity to be equal to unity. So, sometimes the diffusion equation will be written without diffusivity as del squared c by del x prime squared. Okay. And as you will see later when we solve the phase field equations, so typically we do this non-dimensionalization. So, all the parameters that go into the model become 1. Now, you might be wondering what is this characteristic time and what is this characteristic length. Okay, this is something that we do in our day to day life. Okay, non-dimensionalization is something that we do all the time. For example, if I ask you what is the price of this pen, you will say okay 30 rupees. Okay. If I tell you what is the cost of this car, you are going to say 7 lakhs. So, from the unit of rupees, you have switched to the unit of lakhs of rupees, simply because you want to say the number in some small range. Typically, the numbers that we want to tell is between somewhere between 0 and say 100, right. Typically, if you are asked, okay, what is the price of this chalk piece, you will not give that in rupee, but you will say it in paisa, maybe it is 50 paisa, if chalk pieces are still being sold for 50 paisa. And if you say what is the price of this house, I mean somewhere near IIT for example, houses cost in crores, okay. There you do not even use lakhs. For a car you might say 7 lakhs, but when you ask about the home you will say, oh, it is 1.2 crores. So, what we do is that we change the unit in which we refer. I mean there is nothing that stops you from giving the price of the home in pies or the cost of the car in rupees or pies, okay, or the cost of the chalk piece in paisa, right. There is nothing wrong, but we typically do it because we want to get the numbers in some manageable range, and that is between 0 and 100. So, typically this is the number, and if you are very strict it should be between 0 and 1 or 0 and 10, but up to 100 is okay, and beyond that if it goes, you basically tend to change the unit and try to give the answer. So, when we are saying the characteristic time and characteristic length, that is what we mean. Suppose you are looking at diffusion, which is at some micron length scale, right. If you are looking at distances which are measured in microns, if you take the micron out of that by dividing everything by 10 power minus 6, then the number is what you get. On the other hand, you might be looking at diffusion which happens over meters, right, or centimeters. So, depending on what is the size of your material over which you are looking at distance, then you typically tend to take that as the characteristic length scale, right. So, you can think of the system size as the characteristic length, for example. Similarly, suppose diffusion takes 1 day to happen, then it is easier to use as time unit day. Suppose if it happens over some 40-50 seconds, then a day is not a proper unit, seconds is the better unit. Suppose some homogenization requires diffusion to take place over 48 days, then days is better, and some might happen over minutes, then it is better to use minutes. Okay. So, the characteristic time scale again is a time scale associated with the problem with which you are dealing, and looking at the range of times that are involved, typically you take that unit as the characteristic time scale, and that is what we have done. We have done this for two reasons. One is, like I said, all the numbers lie between 0 and 100, and that is always preferable, because when we are doing calculations in the computer carrying numbers like 10 power minus 6, and if it is meter squared per second, and suppose your diffusion distances are in microns and time scales are in seconds, then you will have quantities like for diffusivity 10 power minus 12. So, we do not want to have such very small numbers coming up in calculations, that is one reason. Second reason, mathematically speaking, if you look at this equation, then it tells you that wherever, for example, this d tau by L naught squared, right. This L naught squared could be in microns and this could be in seconds, or this could be in meters and this could be in hours. It does not matter, as long as this d tau by L naught squared becomes some number equal to some k, the solution of the diffusion equation is going to remain the same, right. Which unit you are using does not matter, you can always scale in that unit and you can plot your solutions. Mathematically speaking, there is one non-dimensional equation which you have to solve. If you know the solution, knowing the characteristic time and length scale associated with your problem, you can correspondingly scale and get the right solution for all the problems. So, this again is advantageous, because when I am solving it numerically, I want to solve it just once for different d values, and then corresponding to the actual values that I have for the tau and L naught, then I will get the actual solution. So, it is also much more economical to solve the non-dimensional equation. So, non-dimensionalization is an important process. We will non-dimensionalize all the equations that we will solve, and it is a better way of doing computations, and later I am also going to show that even free energies, sometimes we make them undergo some transformations so that they become far more easier to deal with when we are using computers. Okay. So, we will take a look at some of these things, solving the non-dimensional diffusion equation numerically, and solving the classical diffusion equation, I mean using a couple of analytical tricks. Both we will discuss as part of the lectures that follow this. Thank you.